Hello, this is Luis Rivera. I am going to go over case 5 with imbalance load distribution for this week's DQ1 post. So let's get to it. Solving problems like this makes me a better engineer because it teaches me how to translate real requirements into mathematical models, which is a basic engineering skill that is required. It helps me think in a structured way. I would say it allows me to connect physical constraints to the equations, and most importantly, it allows me to verify that the solutions make sense within the real system. The more we practice this kind of reasoning, the better we are at designing safe and reliable engineering products. So, in this scenario, I'm looking over an unmanned aircraft with sorry guys, it looks like case study 5 is incorrect. Actually, no, it is correct. It's just that no worries. I got confused with the reference, and this still is the aircraft example. Okay, so in this scenario, I'm looking at the unmanned aircraft with 3 payload bays. We have 3 individual weights: weight 1, weight 2, weight 3. The bays sit at distances of 0.5 meters, 1.2 meters, and 20 meters from the reference data as detailed in the problem statement. So we have 3 mission rules we're satisfied. First being the payload, total payload weight of 900 newtons, as detailed here. Total movement created by this weights must be 1216 newtons per meter. This is second coolant rule, and then the third rule would be a packaging constraint that requires 2 bay that carries 150 newtons more than bay 1. So that mathematically means that W2 minus W1 equals 150. Going into part A asks me to write these rules in a linear system and then convert them to a matrix form. So these equations are straightforward. The total weight, as is detailed here, the total momentum is detailed by this equation, and the packaging constraint was previously relayed. I can place the coefficients into matrix A and then the unknowns into vector X, and this will create the compact form of AX equals B, as shown here. In regards to the MATLAB solution, using matrix A and vector B, I utilize a backslash operator, A divided by B, which solves the system that we need, and MATLAB will return the numerical values with floating decimals that it handles as shown here. In regard to part C and asking how I verify the solution, I checked each of the original equations by substituting numbers back in. These need to still hold. So going over the 3 weights adding to 900 newtons, the moments adding up to 1260, and finally the weight subtraction equal our threshold of 150, and the numbers make sense. In addition to just the math, we need to understand whether the signs and the magnitude, make physical sense, right? And in this regard, the weights are positive, the distribution looks reasonable, and the center of gravity requirement is satisfied. So what this allows us is to, when we walk through this step by step, we model the problem, we form the matrix, solve it, and then check the results with our expectations. This reinforces the discipline thinking that makes us stronger engineers or stronger problem solvers, which is what engineer actually is. It will take away the title. It's just problem solving. Thank you, and have a great weekend.